Thank you very much, and also many thanks to the organizers for arranging this wonderful meeting for us. And also thank you for putting together such a nice session with talks that are related, but it means that yet again there will be some repetitions, so I'm sorry for that. Okay, so today I will speak about joint work with David Krejcieřik and František Štampach. And in particular, it will be about these two works that we have together. The first one is a preprint from last year, and the second one is to appear in the Israel Journal of Mathematics. And, so throughout this talk, what you should remember that I will speak about difference operators. So these are actually bounded operators. And also they will act on the discrete half line, so on the natural numbers. And occasionally I will also compare to the continuous case, so to the case of the Dirichlet Laplacian on R+. Okay, let's start with a little outline. First, there will be a short part on motivation, where I will explain how the two notions of criticality and Hardy-type inequalities in the title are related, or actually repeat how they are related. And also there will be a little bit of a point of view on this topic, maybe from the non-self-adjoint angle, and then I will say something about the two works that were on the previous slide in the last two sections of the talk, and in the third part there will be also my very last slide about a recent improvement in the topic by František Štampach and his student. Okay, let's start with the motivation. So let's revisit the classical Hardy inequality, but this time the discrete one. So it is this inequality here. On the left-hand side, you have the L2 norm of the discrete gradient. On the right-hand side, you have a weighted L2 norm of the sequence U with the Hardy weight ρ. And this inequality holds for L2 sequences U, where we agree that U0 should be set to 0, so that I can write here the left-hand side in this nice compact form. And in the classical Hardy inequality, the classical discrete Hardy weight is this sequence, 1/4n squared. And it's very interesting, and a recent development, that even though the continuous version of this inequality that we already saw in Yehuda Pinchover's talk today, there the Hardy weight cannot be improved, but in the discrete setting it can, and this is due to Keller, Pinchover, and Pogorzelski in 2018, where they proved that actually this inequality holds with this weight sequence here, which is strictly larger than the classical weight. And they even proved that this weight is optimal in a certain sense that they specify in their paper, but I will not go into details here. And yeah, this is interesting because it differs from the continuous case. And here in this paper there is, because here they do it in a more general setting on graphs, and here you can find the shorter proof of the inequality with this optimal weight in this special setting on n. Okay, now the point of view that we would like to take during this talk is actually that you can write this inequality also as a form inequality, so you can say this is equivalent to a lower bound on the form of the discrete Laplacian, which is now this semi-infinite matrix here that has these three non-trivial diagonals and acts on a little L2 of n. And then this inequality is just that the form of the Laplacian is bounded below by this weight ρ. And you see that so actually what we want to ask during this talk is existence of such inequalities. We know that for the Laplacian they exist, and we want to discuss whether or not, if you put a power on this Laplacian, so if you think about some positive alpha and you take the alphath power here, do such inequalities still exist or not? Okay, and now what is maybe a little bit surprising is that already for the power 2, so if you take the square of this discrete Laplacian, then there is no analog of the classical Relich inequality, because the classical Relich weight would be some constant divided by n/4, and actually it was proven in this paper by Huang and Ye, that this inequality cannot hold with a positive constant. And even more, you will see from the results that I will present that actually this discrete bi-Laplacian is even critical. So there cannot be any non-trivial, non-negative weight that bounds below this discrete bi-Laplacian. And this is yet another point where the discrete and the continuous case differ, because for the continuous bi-Laplacian there is the Rehlich inequality, which is a lower bound. Okay, before I go into our results, I would like to say a few words about this non-self-adjoint point of view. Because of course so far everything was self-adjoint, what I said, but the title of the conference wishes for more. So if you think about a complex valued sequence, let's say bounded, and you perturb this discrete Laplacian by this sequence, then you can ask the question, what about the spectrum of this non-self-adjoint operator, this perturbation? In particular, when does the spectrum stay unchanged? And then there is this theorem by Krejcik, Laptev, and Stampach that if you have a lower bound for the Laplacian by, now forget about this C, so let's say just modulus of V, then in fact the spectrum of the perturbation by V remains unchanged. So spectrum of this equals the spectrum of the Laplacian, which is in fact only continuous spectrum, and is the interval 0, 4. And if you have this inequality even with a C here that is less than 1, then also you do not get any embedded eigenvalues. So actually then also the spectrum of the perturbation is a purely continuous spectrum. And this relies on a Biermann-Schwinger principle, this result. Very nice general abstract form can be found in this paper here. And if you don't have this C there, so if this C is actually 1, then what happens is that you can also have embedded eigenvalues inside the continuous spectrum. And in fact, here I want to mention that in the continuous setting, this kind of type of subordination condition for the spectral stability was already discovered and used here in this paper. Okay, so let's move to the actual results. So we heard today already many times that what this so-called criticality is about. So before I said criticality means there cannot be any non-trivial, non-negative lower bounds for the operator. So let's rephrase a little bit. A bounded operator that is non-negative on little L2n, we say that it is critical if whenever I introduce a perturbation by minus rho, where this rho is now the weight, so it is some non-negative sequence, then this operator can no longer be non-negative, meaning that there needs to be a negative point in the spectrum. Okay, and now let's repeat the object that we want to look at. It was this discrete Laplacian, that is this semi-infinite matrix on little L2 of n. This is a very nice object. It's a bounded operator with this spectrum, this interval, as I just said. So I can define by functional calculus simply the powers of this operator. So I want to take a positive alpha, and I want to ask what happens to this power, minus delta to the power alpha. And what we found out that actually these powers are critical if and only if alpha is larger or equal than 3/2. So between 0 and 3/2, they are subcritical, so-called subcritical. So these Hardy-type inequalities exist, and when you make alpha sufficiently large, so 3/2 or larger, then they become critical, and these inequalities no longer exist. Okay, so this again differs from the continuous setting, where for the polyharmonic operators actually the so-called Biermann inequalities exist, where there is a lower bound on this continuous polyharmonic operator by this Biermann weight, which is 1 over x to the power of 2 alpha. So alpha is the power in the polyharmonic operator, and there is some constant in front which is optimal. And of course, for alpha equal 1, this is just Hardy. For alpha equal 2, this is the so-called Rehlich inequality. But it holds for any alpha in n. And okay, so this is, here you see that there is certain discrepancy, because here for any alpha you have these inequalities, but I'm saying that here for large alpha actually you cannot have any. Okay, and now a bit of a different setting. If you look at the discrete Laplacian on the full line, so on Z, then these type of questions were already studied. And actually, Chiauri and Roncal, they found for alpha between 0 and 1/2, they found Hardy-type weights, and they even proved that they are optimal. No, sorry, in this paper, in the second paper, it was by Keller and Nitschmann, it was proved that they are optimal. And if alpha is larger or equal than 1/2, then actually you can repeat our procedure to show that the powers become critical again. Okay, so I would like to say a bit about our strategy and also where this threshold comes from, this 3/2. So again, if you remember, criticality is about whether or not, if you perturb, whether or not for an arbitrarily small perturbation, a negative spectral point emerges on the left of the spectrum. So a good idea is to look at the Biermann-Schwinger principle. And for this, we want to think about, again, a bounded weight sequence rho, non-negative, and a negative point lambda that we want to investigate if it's in the spectrum or not. And now the Biermann-Schwinger principle says lambda is in the spectrum of the perturbation if and only if -1 is in the spectrum of the Biermann-Schwinger operator, which is the free resolvent sandwiched essentially between the square root of the weight. And now it turns out that the criticality or subcriticality is related to the matrix entries of the free resolvent and how they behave when lambda tends to the spectrum from the left, namely if for all n the diagonal entry in the matrix representation of the resolvent blows up. So the NN entry blows up when lambda tends from the left to the spectrum, then one can prove criticality. On the other hand, if this does not happen, so if actually for all Mn, so if all matrix entries of the resolvent are uniformly bounded in lambda on the negative half axis by some constant that can depend on the respective entry in the matrix representation, if this constant is somehow suitable, then you can prove subcriticality. So you can derive a certain Hardy-type inequality that will depend on what is the bound here that you get. It will depend on the CMN. Okay, and so for this, one needs to investigate the free resolvent. And very conveniently here, this discrete Laplacian is unitarily equivalent to a multiplication operator on a certain weighted L2 space. So there exists this unitary U and some weighted L2 space, and it's equivalent to multiplication by 2 times 1 minus x. So if I want to put the alphath power, I just put it on this function. It will be unitarily equivalent to 2 to alpha, 1 minus x to alpha. And then also using this relation, you can actually compute these matrix entries of the resolvent, and they look like this here. Here, this UN, these are Chebyshev polynomials of the second kind. And here you can see where the exponent 3/2 comes from, because if you want to know the behavior as lambda tends to 0 from the left, then you can think about just putting here lambda equals 0. Now, these polynomials here, they don't change anything about the singularity at 1 that we have here in this integral. And actually, the integrand behaves like 1 minus x to 1/2 minus alpha. And this is where this condition comes from, namely, this for lambda equals 0 is integrable if and only if alpha is between 0 and 3/2. So this is when you get the subcriticality. Okay, now in this subcritical regime, so now for a moment think about alpha in this subcritical interval. I said that we obtain a certain Hardy-type inequalities, namely we get existence of some constant that depends on alpha, such that we have a lower bound by the weight rho that is either constant over n to 2 alpha if alpha is not 1/2, or here, if alpha is 1/2, then you have to still multiply with the logarithm. So then it looks a bit different. And this is let's say, the optimal expected decay rate of a Hardy-type weight, because if you think about alpha equal 1, this is the classical Hardy weight at infinity. And also, if you compare it with the continuous setting for the fractional Laplacian, it was proven that the fractional Laplacian for alpha between 0 and 1 admits a lower bound rho, which is of the form 1/2 alpha times some constant kappa alpha, and depends on alpha. So here again you have the same power, at least for alpha not 1/2. And interestingly, also what happens here, that when alpha is 1/2, this kappa alpha is actually 0. So also there something different happens for this exponent, 1/2. So it's not surprising that we also cannot get here only 1/n. Okay, and now I want to emphasize that actually, except in the case alpha equal 1, where there is the Keller-Pinch-over-Pogorzelski optimal weight, for other powers we do not have optimal weights. And actually we don't even try to optimize this constant, because we know that this type of weight is anyway, even for alpha equal 1, not optimal. So still it remains open to find optimal weights in this subcritical regime, except for alpha equal 1. Okay, let's move to the second main part. I said that when you make alpha large, in principle there are no Hardy-type inequalities, but actually what you can do is, if you restrict to a certain suitable subspace, then on this subspace there exists still the discrete analogues of the classical Biermann inequalities. From now on, think about alpha being integer, and what holds there is that this discrete polyharmonic operator is still bounded below, but now this is the discrete version of the Biermann weight on a certain subspace, and this subspace are all L2 functions where the first alpha minus 1 entries are 0. And this was proven by Huang and Ye, and by Gupta with a smaller constant. Now this space might seem somehow strange, but actually it is, you can view it in some sense as a continuous analog of the space H0 alpha on the half line, which is the space of all H alpha functions, or Sobolev functions of order alpha, where the first alpha minus 1 derivatives at 0 are 0. So you can make sense of this, and then it is not surprising that this inequality holds on this discrete version of the space H0 alpha, because also the continuous version holds on H0 alpha. So this makes somehow sense, and what we proved here is that in the Relich case, so for alpha equal 2, we have a lower bound by a weight that looks somehow on the space H02. And maybe the important part is that it is strictly larger than the classical discrete analog of the classical Relich weight. So it is an improvement on this subspace. Okay, so a little bit about our strategy. It is for this inequality, it is based on a description of the remainder in the Hardy, let's call it equality. So a formula for the remainder in these two papers. In the second one, there is an abstract version of it. And now in this case, in this Relich case, it looks as follows. So the square of the Laplacian is now this semi-infinite matrix. So it has 5 diagonals. It is almost only 6 minus 4 and 1, but there is here in the left upper corner, you have a 5 instead of the 6. And the idea is that, okay, you have your weight, which is given somehow, which I will say more later about. And if you subtract it from this by Laplacian, then here on the left you have some pentadiagonal, so 5 diagonal matrix, and this should now be non-negative for the inequality to hold. So the ansatz is that this is some R star R, and this operator R should look like this, that you have some sequence on the diagonal A, and then above you have two more sequences B and C. So this is an ansatz that we make. And of course, if this is true, then here on the right-hand side, this is a positive operator and the inequality holds. And we were not able to compute explicitly these sequences, but we could show their existence and also their asymptotic behavior, and this was enough for our purposes. And in fact, here I want to say that this weight is not optimal in the sense of Keller, Pinchover, and Pogorzelski. There are three optimality properties that need to be satisfied. Two of them we were able to prove, the third one not, and not surprisingly because actually it doesn't hold. And the weight was improved by Huang and Ye later. Still, I want to say a little bit about how we even constructed this weight. So the idea was this so-called super solution construction, which can be found for second order differential operators in the continuous case in this paper, and which was also employed a discrete version of it to actually obtain this improved Hardy weight. And the idea is to choose a sequence G, which is in this case, which is annihilated by the operator, so which is in the kernel, let's say, of the operator, and to plug it with the square root in the operator and divide by the square root. So this is how to construct the weight in this way. And of course, this is a second order operator, so a good thing to choose is first order sequence, so just n to power 1. And this is how this weight came to being. So we kind of adapted this and we said, okay, if you have the square of the Laplacian, so then take for the sequence G n to the power 3, because this is a fourth order operator, so take here the power 3. This is how we chose our weight, and it worked. So the inequality really holds with this weight, and this is what led us to conjecture that actually the Biermann inequality, so lower bound for the alphath power, alpha integer, holds on this special space H0 alpha with the weight again constructed in the same way, and now the sequence to be n to the power 2 alpha minus 1. Because this guy here is a difference operator of order 2 alpha, so if I apply it to this, it will make it 0. This was our conjecture. We did not prove it because this strategy with the remainder factorization, it becomes increasingly difficult if you raise to a higher power alpha, because the remainder is then a difference operator of order alpha. But what we did prove is that if it is true, then it would improve upon the classical Biermann weight. And now the last slide is this nice improvement that I was already advertising a little bit, because in fact Franciszek Stampach and his student very recently uploaded a paper to arXiv where they prove that in fact the Biermann inequality, again same equality as in the conjecture, it holds on this space with a weight that is constructed in the same way as before, but with a different G. We had here another G, so they adapt this G, and they even show the optimality of this weight. Now, they also prove that this improves upon our conjectured weight. In particular, they prove the conjecture. And yeah, as I said, we had a different G. This G was just n to the power 2 alpha minus 1. So here you see, if you don't put here this minus j, then you just get our conjecture back. But they improved it, and even it is optimal. And a little bit about their strategy is that what they did is that they in fact used a formula that was proven by Huang and Ye, which is a weighted version of the remainder identity by Krejcir, Lapiev, and Stampach, which actually we based our Relich approach on. It's a weighted version of that. So if you put here this omega is a weight, if this omega is 1, then you get back the identity that we used or that inspired us. Okay. Now in this formula, it's not important how it looks. This is the discrete gradient and the discrete divergence, and then the Laplacian is just minus div grad, and they applied this formula iteratively, and in every step they chose a different weight, and in this way actually they were able to prove a similar identity but for arbitrary order, and they proved that their sequence G is such that on one hand the remainder is not negative, and second that the weight that they obtain is positive and actually optimal. And this gives a very nice and round picture or solution to this topic, and this is all I wanted to say, and I thank you very much for your attention.
Thank you very much. Are there any questions for the speaker? Please.
I think it was at your first page you mentioned that like for some alpha the Hardy inequality does not hold, but it would hold in the continuous case. So do you have maybe some intuition like what actually gets wrong, like to compare these two cases, or it's just like, okay, there's one computation, there's another one, and the methods are so different that one cannot really see what first slide, I think.
Was it here?
No, the slide number 1.
Oh.
This one, discrete, is not the same as continuous.
Yes.
Sorry, it's for the by Laplacian, yeah.
Yes, so actually this is a special case of this one for alpha equal 2, where for alpha equal 1 it holds in also in the discrete case, but if alpha, if you start to make it large, then the operator becomes critical. But actually, so my intuition is that maybe you need to look at a different operator in a way, and this is the second part of the talk. So you need to, if you want that there is an analog of this inequality, you need to restrict to the correct subspace. So this is somehow the intuition, because if you think about it, also the continuous bi-Laplacian is also not the square of the continuous Laplacian. So you put some other domain in principle, and now it's of course tempting because you deal with bounded operators to just put the power, to take power 3, 4, etc. But it's not what happens in the continuous case. So the intuition is that this is the difference, and that maybe if you really want to compare the two cases, you need to do it on these subspaces that I wrote here. So these continuous inequalities, they hold on this subspace. On this subspace. And if you introduce a discrete version of this subspace, then also the discrete ones hold. But they just don't hold on the full space. Or on the full space, you cannot have any lower bound. Does it make sense?
Any other questions? I actually had one very small question. Yes. At some point, you mentioned that this fractional Laplacian is unitarily equivalent to some multiplication operator. Mm-hmm. I was just wondering, what's the nature of the unitary transformation?
It is this. So the space is L2 of the interval -1, 1 with this weight. Okay. And you map the jth, let's say, basis vector, so the sequence that is 0, 0, 0 and 1 at the jth entry, you map it to the Chebyshev polynomial uj.
Yeah,
yes.
If there are no other questions, let's thank the speaker again. Thank you very much.